Okay, it's time to start thinking about redox again. This is topic 14. And before we get into new material, obviously we need to recap older material. You've known about oxidation numbers and oxidation states since year 10. Last year you put them to good use. This year we're going to take it to a new level, obviously. So let's recap the basics for calculation of oxidation numbers or states. Numbers and states we take to be synonymous. So the group 1 and group 2 metals are invariable here, aren't they? They are always +1 in group 1 and always +2 in group 2. So they are the reference elements in calculation of oxidation states and numbers. The only other that doesn't change is fluorine. To do with its electronegativity, we gave it priority and it's always -1. So oxygen is usually -2. The exception with fluorine it would be +2 because each fluorine is -1 and there are two of them. So it's +2 here. In metal hydrides, hydrogen is usually +1, but in metal hydrides like sodium hydride or potassium hydride, it's -1. And chlorine, it says usually -1, but we've seen lots of examples of when chlorine isn't -1. It's been 0, +1, +5, you get +6s. Okay? When it's mixed with oxygen and fluorine, obviously, that's when its oxidation states can change because these two would take priority over it. So try and remember those basic rules. Another simple idea, the idea that a reducing agent is oxidized. It reduces the other thing. The oxidizing agent is reduced. So a reducing agent reduces an oxidizing agent. Okay, they're two sides to the same coin. Yin yang. Reduction is a gain of electrons, isn't it? So if it gains electrons, it's reduced here. And if it loses electrons, it's oxidized. Oxidation is a loss of electrons. So these two electrons here are being given to B, and B is reduced. Okay, let's get that clear in your head. Other things to remember. Equations, you have to write equations and half equations, ionic equations, and show how the electrons are transferred. So your half equations are going to be very important. Redox with stoichiometry, we can actually use redox, the number of electrons transferred, to help us balance equations. And titrations, you can do redox titrations in the same way as you can do acid-base titrations. Oxidizing agents, 3 classic oxidizing agents we've come across: potassium manganate 7, potassium dichromate 6, and chlorine. You have to be able to write the half equations for these, and they are good at receiving electrons. Okay, they accept electrons, don't they? The half equations, you can have a go at them now. I'll put them up in a few seconds. Okay, potassium manganate 7, so that's the half equation, dichromate 6, and chlorine. Okay, reducing agents, the easiest ones to remember are reactive metals. So reducing agents must be good donors of electrons, mustn't they? They give electrons up. Reactive metals such as magnesium, potassium, sodium, they're all good donors of electrons. So they're good reducing agents. Now, we now need some way of comparing how good something is at reducing or oxidizing. And we're going to use something called the electrode potential scale. And this is what it looks like. Oh, no, it's going to come up soon. So let's remember from IGCSE, GCSE, something as simple as a displacement reaction, we've seen that this is redox. And we can split this reaction into two halves, can't we? The oxidation half equation and the reduction half equation. Okay, so electrons have been transferred in this reaction. Zinc is losing its electrons to become Zn2+. Oxidation is a loss of electrons, so it's going from an oxidation state of 0 here to an oxidation state of +2. This is its reduced form. That means it can give its electrons to other things, so it can reduce other species, and in the process it's oxidized. And in its oxidized form, it could potentially oxidize other species. The same could be said for the copper. Copper 2+ gains electrons here and becomes copper. Its oxidized form, +2, becomes 0. In its oxidized form, it can oxidize other species when it gets reduced, and when its reduced form, it can reduce other species when it gets oxidized. Now notice that we used equilibria symbols for these equations now. Okay, so each half equation has an oxidizing agent and a reducing agent. Let's have a look at some more. Sodium is a good reducing agent. It loses electrons, giving those electrons to other things. So sodium Na+ potentially could be an oxidizing agent. Now that might not seem very likely, but there are contexts in which it potentially could be forced to take its electron back. The chlorine here gains 2 electrons, so the chlorine is the oxidizing agent. Chloride could potentially be a reducing agent. It's a bit like the Lowry-Bronsted acid-base pair, isn't it? And the relationship is mediated by an electron or by electrons, just as it was mediated by protons in that theory. This is the table of standard electrode potentials. Okay, and it's a comparison at how good things are at accepting electrons, essentially. Okay, so you can see here on the left hand side, this is all something accepting electrons, and then you have a scale according to how good they are at doing that. The more positive it is, you can see, the more likely it is that it will accept an electron. Chlorine's desperate for electrons, isn't it? Whereas potassium ions, well, it's going to be more difficult to get them to accept electrons. Identify the strongest and weakest oxidizing and reducing agents. We'll do that in a second. We're going to draw arrows to show the trends, and we'll discuss the Allen anti-clockwise rule. That's me. It's my claim to fame. One has to try to be immortal some way. So, strongest and weakest oxidizing reducing agents. Now we've already said down here, what did we say chlorine was a few slides ago? Chlorine is a very good oxidizing agent, isn't it? So chlorine, manganate 7 we looked at, fluorine, they're all good at accepting electrons. We also mentioned the idea that reactive metals were good reducing agents. So the best reducing agents are up there. So clearly the trend is going to be, these are the worst oxidizing agents. They get better as you go down. These are the worst reducing agents, and they get better as you go up. Be careful with these tables. Sometimes they change the order. It should have the electrons on the left-hand side. So this is the oxidized form of each of these things, these species. And it should have negative numbers at the top and positive numbers at the bottom to be able to use it in this manner. It doesn't have to have it, but it's just easier to remember the rules that way. And that means that the anti-clockwise rule works. So the natural tendency here is for things to go anti-clockwise. So what do I mean? I mean, if you put calcium with chlorine, then the calcium is going to become Ca2+, and the chlorine is going to become Cl-. So the tendency is for the equation, the half equation at the top to go to the left and the half equation at the bottom to go to the right. Think about that. Scale represents a tendency for oxidized state to accept electrons. We said that. The greater the positive value, the greater this tendency. And then try to remember species at the end of the scale. So potassium's right at the top, and it's got a very negative value. Potassium is a good reducing agent. Chlorine's at the bottom, it's got a very positive value, and chlorine is a good oxidizing agent. Okay. This shows the spontaneous tendency. If we put these things together, these two half equations. So if we get a closed system, we put some potassium ions, some potassium, some chlorine, and some chloride ions, then the tendency is for the top equation to go to the left and the bottom to go to the right. Spontaneous tendency. Ooh, spontaneous. Sounds a bit like entropy, no? It will come into this at some point. These are called the standard electrode potentials, and they're measured by placing them in a cell, a system, with the standard hydrogen electrode. Okay, so what we do is you set up a system where the standard hydrogen electrode is the left-hand half cell. This is called a half cell, and it consists of platinum plate. This is platinum. Okay, platinum obviously conducts electricity. It's inert. It's also quite a good catalyst. It doesn't react, but it does help the process to happen. 1 molar solution of hydrogen ions and 1 atmosphere hydrogen gas is pumped into here. 298K, and everything's standard. We make this the left-hand component of the cell. The right-hand component, or the half cell, corresponds to the electrode potential to be measured. So here, for example, I've got copper metal in contact with copper ions with 1 molar concentration. This is a salt bridge, which just completes the circuit, so electricity can flow, and you measure the voltage V. So in this case, the voltage would be, if you look back at the tables, the voltage would be positive for the copper. Okay. Now, it's a standard electrode potential if the standard hydrogen electrode forms a left-hand cell, concentrations are 1 molar, gases present are 1 atmosphere, so 100 kilopascals, and temperature 298K. Remember, changes in concentration and temperature, they will affect the rate of reactions, but not the likely direction of reaction. Okay, so effects of these changes are going to be quite small, but the voltage of the cells can be slightly changed. Now, cells. This is where cells come from. You take 2 half equations and they produce electricity, an electric current. So in general, the half cell with the more negative standard electrode potential produces electrons. It gives up electrons. And obviously the half cell with the more positive accepts them. Okay? So the more negative is the negative pole of the cell. The more negative is the negative pole, and electrons flow in the circuit from the negative pole to the positive pole. The more positive accepts the electrons. The Daniell cell. This is one of the classic cells that was investigated initially when these processes were discovered. And the Daniell cell essentially is zinc in a solution of zinc ions, copper in a solution of copper ions, and then we have a salt bridge, which in this case is potassium chloride, which just helps the electricity to flow. So electrons are produced at the zinc and they flow around the circuit to the copper. This is why, because there's electrons at the copper, it's often called the cathode, and the place where the electrons are made is called the anode. I would call this the negative pole of the cell, and the copper is the positive pole. Now, how does that work? Well, it's the positive pole because conventional current goes in the direction opposite to that of the electrons through a cable. So the conventional current here is going this way, and conventional current in a circuit goes from the positive pole of a cell or battery to the negative pole. So the more reactive metal is always the negative pole, and the negative pole is considered to be the anode also. The positive pole is considered to be the cathode. The Daniell cell. You can see the chemical reactions. There's zinc. The zinc is up here using the anti-clockwise rule. The top equation is going to go to the left, and the more positive electrode potential further down goes to the right. Okay, so zinc becomes zinc ions and copper ions become copper. And they produce an EMF, an electromotive force, a voltage. You can represent this cell. This is just a bit of symbology, but you can represent it like this. So you've got the more positive of the half cells is on the right hand side and the more negative on the left hand side. These dots here are considered to represent the salt bridge. There are a few rules to follow here. We'll talk about them now. So by convention, more positive is on the right hand side, apart from the exception is when you're measuring the voltage of a half cell compared to the standard hydrogen electrode. The vertical dotted lines represent the salt bridge. The oxidized forms are written next to these dotted lines. So this is the oxidized form of zinc, and this is the oxidized form of copper. The EMF of the cell is calculated using this equation. It's the right-hand electrode's standard electrode potential minus the left-hand electrode's standard electrode potential. So here, that's the calculation. This is the standard electrode potential of copper minus the minus 0.76 of zinc. It gives me 1.1 volts, which is what they found when they investigated the Daniell cell. Okay, that's a lot of information to start thinking about. Read the pages indicated and do any questions that you come across. Let this sink in.